Hello everyone, this is the presentation about the effect of annealing temperature on the properties of nickel oxide and gallium oxide heterojunctions fabricated by thermal oxidation. First of all, what are we doing and what are we concerning about? We need to have some background. For years, the power device market is dominated by silicon, from the rated voltage below 650 volts to over 3,300 volts. Researchers are trying to replace silicon with some candidate with potentials in whether performance or cost. Among these, gallium oxide is a good choice for the high voltage environment. Beta gallium oxide offers major advantages: a wide bandgap for high voltage performance, excellent dopability, a high Balagas figure of merit, and low cost. However, its key limitation is an inability to achieve p-type conductivity. Therefore, forming a heterojunction is essential. Nickel oxide is a leading candidate for this role due to its p-type conductivity, suitable band alignment, and good lattice match. We plan to study nickel oxide formation on gallium oxide by thermal oxidation, varying the temperature. The process has three steps. First, depositing nickel onto a GaO wafer. Second, annealing it in oxygen using RTP equipment. And finally, allowing the nickel to fully oxidize into nickel oxide. The figure below shows the fabrication results. We set 4 different annealing temperatures to observe the oxidation process. From visual observations, we can already see that the nickel is successfully oxidized because the opaque nickel on gallium oxide has turned into a transparent material. Then we'll perform several characterizations of the nickel oxide thin film. AFM analysis shows our deposited nickel film is exceptionally smooth. After annealing to form nickel oxide, roughness increases over tenfold. This significant change occurs because the heat treatment crystallizes the film, forming distinct NiO grains and new boundaries. Therefore, the increased roughness confirms the successful transformation into a polycrystalline semiconductor oxide. Our XD results show a clear temperature-dependent transformation. At 300 C, the film remains partially metallic nickel. At 400 C and 600 C, oxidation is complete, forming pure nickel oxide. Crucially, the stronger peak intensity at 600 C confirms enhanced crystallization. This demonstrates that while 400 C is sufficient for full oxidation, higher temperatures provide the necessary thermal energy to significantly improve the crystallinity of the NiO film. Our SEM results show that the 80 nanometers nickel oxide film is too thin for clear imaging, making the interface difficult to observe. Consequently, the accompanying EDS data is too blurred to reliably analyze element diffusion. To properly study this, we require higher resolution characterization, specifically using transmission electron microscopy or a higher resolution SEM. Our diode electrical measurements confirm the structural findings. The 300°C sample shows Schottky behavior, low threshold voltage, and high leakage consistent with residual metallic nickel. In contrast, samples annealed at 400°C and above exhibit higher threshold voltages, confirming full oxidation to nickel oxide and the formation of a true heterojunction. Among these, the diode fabricated at 500°C demonstrates the best on-state current, identifying it as the optimal processing temperature. In a conclusion, to form the heterojunction, annealing above 400°C is necessary for complete nickel oxidation. Higher temperatures, like 600°C, enhance crystallization and increase surface roughness. Electrically, this transforms the interface. 300°C leaves metallic nickel and poor performance, while 500 to 600°C creates a true crystalline PN junction. We find 500°C to be the optimal condition, successfully forming a high-quality P-nickel oxide and N-gallium oxide heterojunction with excellent rectifying properties. Thanks for watching.